Thanks for tuning into this talk, where I'm going to summarise my PhD research. So the original title of my project was going to be a laboratory study on internal sultry waves in ice-covered waters. As you can see from my new title, Experimental and Numerical Modelling of Boundary Effects on Internal Sultry Waves, this changed quite a lot. And by the end of this talk, I hope that you'll understand why I pursued some of these directions and understand some of the key outcomes of the project. But before I start talking about my work, I'm going to take a minute out to explain what internal sultry waves are and why we care about them interacting with the boundaries. So internal sultry waves are internal in the sense that they travel along density interfaces within stably stratified fluids. And from now on, I'm going to refer to these density interfaces as the picnic line. They're solitary in the sense that they do not merge and their speed depends on their size. So here you'll see a train of internal sultry waves with the largest out in front because they've separated out due to that speed effect. And because they're waves, they're able to travel long distances without change of form. So in the ocean, they're responsible for transporting the important things that we want to know about as oceanographers. So that includes mechanical and heat energy, sediments, nutrients, fresh water and salinity. But they only do interesting things with that when they interact with the boundaries. So with my background in marine biology and oceanography and polar oceanography, I was kind of interested in these broad questions around how heat, nutrients, and other things are moved around the ocean, how this would affect marine ecosystems, and how it would cause the melting of sea ice with the specific problem of the Arctic Ocean. And we addressed these through a laboratory study where we reduce the system where we have internal waves on a stratified interface in the ocean down to the laboratory scale. So here we have salty, dense water at the bottom, overlaid by fresh, lighter water. And behind a removable perspex barrier at one end of the tank, we have a further volume of that fresh water, so that we have a discontinuity in the picnic line. On the far end of the tank, we insert something that we're going to investigate the interaction with, and in this case, I'm showing sea ice. Upon removing the perspex barrier, we get an internal wave propagating down the tank from right to left until it interacts with this object, and that's when we're going to observe it. Now, my thesis was initially intended to be primarily laboratory-based, but not long in, COVID hit and we closed the lab. Part one of my project changing was that we ended up being really lucky to add in numerical modelling. So we used the numerical code SPINS, which solves the incompressible Navier-Stokes equations in a configuration that matches the lab very closely. We had previous validation of this to show that this would be a good model to use to match what we have in the lab. But back to the lab. You'll see here a time-lapse video of me setting up the experiments. So we begin by filling the lower layer of the tank with salty, dense brine before we leave it overnight and then add in an array of sponges in the next morning through which we drip feed the less dense water from above so that we get a nicely separated two-layer flow. And the sponges and the drip feeding helps make sure that we minimize the mixing between the two layers. So you can just about see on this image in the middle here, we have the interface between the two. As we reach 7 centimeters depth in that upper layer, we remove the sponges from this end of the tank, but insert the gate and continue filling behind the gate until we reach the total depth of 30 centimeters. Once we've done that, we take measurements of the density profile using a conductivity probes, and then we add in this case, our ice and our seeding particles so that we can visualize the flow. So then we turn off the lights once we're ready to run the experiment. We start the cameras and we turn on a vertical light sheet through the center of the water column. When we remove the gate, we generate the wave, and we're then able to visualize this using these three panels here. So the upper panel shows the raw image that we see in a black and white camera. The middle image is then the false color scheme of that same image, which we use to visualize, and that's what you're going to see throughout most of the rest of this presentation. And below it is the output of the particle image velocimetry, which shows us the horizontal and vertical velocities associated with particle movements. So to get started in the lab, I began with some experiments of internal solitary waves propagating up slope, a process that we're now going to refer to as shoaling. Preliminary experiments had shown that there was something interesting in this project around how waves shoaled in a different stratification, specifically one that can support trapped cores. But this was ideally meant to just be a training project, which would get me started with some interesting experiments to start with. So the background of this is that previous studies have identified a system of 4 different braking types, depending on the combination of the slope steepness and the wave steepness, where the wave steepness is the amplitude divided by the wavelength. And this breaks down into 4 different regimes: fission, surging, collapsing, and plunging. However, all of these studies have followed a similar stratification type where we have a well-mixed upper layer, a well-mixed lower layer, separated by a thin pick incline. So we're going to refer to this case as the thin pick incline case. However, in the real-world ocean, we have many more different types of stratification, and we wanted to explore how some of these different types might affect the dynamics. We started off by expanding this pick incline throughout the surface layer. So we now have a 7 centimeter thick pick incline, and beneath that a well-mixed lower layer. And we're going to call this the surface stratification case that we tested initially in the laboratory and later in the numerics as well. And then later on, we also investigated what we're going to call broad stratification, where we continue to extend the stratification throughout the entire water column. So we had this new lab set up, and this is what we were able to create. We have a wave coming in from right to left and begins to interact with the lower boundary. We get the formation of a shear layer and a vortex, which drags the pick incline back on itself and causes it to collapse, hence the name of the collapsing breaker. That bolus then moves up slope to a location far up slope of where it would initially have rested. And as I mentioned, we also carried out these experiments in the numerical model. So here I'm showing the horizontal velocities overlaid with the contours of the pick incline. We see again this picture of the wave coming in, interacting with the boundary and this vortex structure being formed and causing the pick incline to collapse in on itself. So you see good agreement between those two cases. But what's interesting is that if this had been in the thin pick incline case, it would have been in the regime indicated by the yellow highlighter here. That is, it would have been a plunging case. We're plotting this in the surface stratification. We found through a series of experiments and modeling simulations that actually we were unable to form the plunging at all in the surface stratification, regardless of what regime in the this diagram we found ourselves in. Instead, because we had stratification throughout the upper layer, that stabilized the instability that normally would cause a plunging type instability. So interestingly, when we then extend this further into the broad stratification, we're also unable to form the collapsing breaker type that I just showed you. And as you notice, that instability forms on the lower boundary. So as a result, when we have stabilizing stratification on the lower boundary as well, we're also unable to form collapsing breakers. And instead, we find surging across this entire regime. Going back to these questions that we were interested in from the start about the movement of heat and nutrients, we wanted to understand more about the mixing that would be induced by these different internal solitary wave breaking types. I was supervising a master's student extending my shoaling work to cover rough slopes, and we identified some strange things happening in the mix diagnostics. Specifically, that we were getting both positive and negative measures of mixing, which is meant to be an irreversible process, so we should only be able to get it positive. So I went over to Canada to work with Marek and the group who work on spins over there to try and understand a bit more about the problem. And whilst I was there, we came up with a new mixing diagnostic tool, which we called user-defined scatter plots, or USP. So to explain what these are, we start off with two variables that come out of the model. Here I'm going to show density and kinetic energy, but we can in fact choose any two variables depending on what it is we want to understand. We plot on density kinetic energy space, where each grid point in the original model output falls. And we split this up into bins, and we sum up the volume associated with each of those bins to produce the user-defined scatter plots shown on the right. From here, we can see immediately that we have a lot of kinetic energy associated with the high and low densities, which is what we might expect looking at these diagrams, where the intermediate density is associated with the picnic line, or where we have high shear and therefore very low kinetic energy. But interestingly, we already see that we've got something interesting going on here with this high kinetic energies associated with the intermediate densities, indicating there might be mixing taking place here. So we want to go back to physical space here. So we select the region of our USP that we're interested in, and then we can identify where in physical space that is represented, which tells us more about where and how mixing is taking place than previous measures, which would tell us more about how much. So connecting this back to the shoaling work that we've done, I show here quickly 4 different wave breaking types that we investigated. And you can see that the regions of interest that are highlighted vary differently between the different wave breaking types. So for example, in the surging type on the left, we've got a very small area of mixing taking place, whereas the fissioning is extended over a very large horizontal domain. Now, once I'd finished with all of this and I was back from Canada, I was able to focus on the question of how internal sorption waves interact with sea ice again. As I mentioned before, we're really interested in how heat moves around the Arctic Ocean, and in particular, how that might then interact with sea ice. So I wanted to model the motion of sea ice under the influence of internal sorption waves. I did this in the lab with polystyrene blocks representing the sea ice, and they're weighted so that they have the same density difference to the upper layer. And the two interesting things that we want to observe here are that, firstly, the ice moves under the influence of the internal sorption wave, and we want to understand more about how, and also that there are flow features associated with the underside of the ice, and again, we want to understand more about them. So I was able to produce a simple model to understand this movement of ice. And here we were able to validate this against the laboratory experiments. So I had our simple model, and we also were able to understand the flow dynamics as a result by understanding the interaction of a moving floating particle and a moving flow field. And it was only by comparing the flow field in relation to this ice motion that we were able to understand these flow dynamics. Together, these come back to having a better framework that we've developed for understanding the real-world complexity of sea ice and internal sorption waves. For example, higher concentrations. So coming back to an important question as to what's new in my thesis that we didn't know in science before. Well, to start off with, we have more validation of combined numerical and experimental internal sorption wave studies, in particular in this new context of wave shoaling. We now know that the fundamental dynamics of wave shoaling depends on stratification, and this will allow us to better implement these mixing ideas into our numerical models in the future. We can also understand where and how mixing occurs, and with this new technique of USP, we can include traces and other things that we might be interested in, and it's a really interesting new method of thinking about your data. And finally, we have a better framework to understand ice internal sorption wave interactions, and this may well be applied to other structures that we might find in the ocean as well. So thanks for listening.